Welcome to part 10 of revising for the specialist exam. Now, I've travelled all around Australia, I've checked all of the past papers. Today I'm going to show you some questions that wouldn't look out of place on the specialist external exam. Let's go.
Okay, first question here from Victoria in 2010. Give yourself 90 seconds. I'm going to solve it in 3, 2, 1. Let's do it. Alright, so we've got a dx dt and then a function with respect to x. So it's going to be easier if we flip that over. So dt dx equals 1 over that. And now we want just a function in terms of t and x. So we'll integrate this. T is going to be equal to the integral of that. So the integral of that is going to be equal to 1 over negative 0.15 ln x and then a plus c there. Alright, all of our answers you can see don't have this negative 0.15 going on here. We can rewrite 1 over negative 0.15 as negative 20 over 3. So it's at this point you'd normally think about initial condition, but we're not told how much of this drug is in the patient's system at any given time, right? So we're going to say at t equals 0, let x equal just some random variable, say a. And we can sub that in. If we've got that, we've got 0 equals negative 20 on 3 ln a plus c, which tells us that c is equal to positive 20 on 3 ln a. Okay, and we can proceed from there, right? Because now we want to know after how long will the amount of drug be halved. So t is equal to negative 20 on 3 ln. Let's halve that drug. So we've got a on 2, right? A was our initial condition. There. Plus 20 on 3 ln. All right, so let's take a closer look at this one. We can bring this negative up to there, because if we do that, we'll have a 20 on 3 for both of those to the negative 1 plus 20 on 3 ln a. Alright, so I'm going to do three things here at once. 20 on 3, 20 on 3, so that's a common factor that comes out the front. We've got, in these brackets, we've got ln a over 2 becomes 2 over a with that negative power plus ln a. And we can bring these together. To be 20 over 3 ln 2a over a. And this a magically vanishes now. So we've got 20 over 3 ln 2, 20 over 3 ln 2. My answer is B. Next question.
Okay, give yourself 90 seconds to solve this question. It's from Victoria in 2012. Alright, I'm going to solve this in 3, 2, 1. Let's go. Alright, there is some kind of graph. I don't know what it looks like. And I'm rotating it about the x-axis to find a volume of solid of revolution. And it's that rotation that's going to be important. I don't know what terminals to use. No one told me about that. So, when in doubt, why don't we graph it? Oh, hello, I've graphed it. It's a half a circle from negative 2 to 4. Wait, is this actually a circle or does it just look like a circle? Well, looking at that, I guess I could rewrite that as y squared equals 9 minus x minus 1 squared, which I could write as 9 y squared and x minus 1 squared with a plus there. Oh, it is a circle. It's a circle with radius 3 and a center of x equals 1. That is what that is. So if I didn't have a calculator, this feels like maybe I should know how to do this. So let's think about the volume of solid of revolution. The volume of solid of revolution is equal to pi, the terminal, so we know we're going between negative 2 and 4, of the function, so root 9 minus x minus 1 squared with respect to x. Okay, I need to square the function. Alright, so the square root of a function squared, that means I can get rid of the square and I can get rid of the square root. Okay, so I believe the volume of solid of revolution is pi 4 to negative 2, 9 minus x minus 1 squared with respect to x. Let's take a look. It's not this because it's still got the square root there. And it's not this because there's like the square root we've got rid of twice. Okay, it's not that one. Okay, it feels like it could be this one, but then the terminals are swapped around. That's a problem. Specifically, the terminals are like here and like over here, which means you're going to be rotating a function that doesn't even exist. So, okay, that's out. Between 3 and negative 3, that doesn't make sense either. I'm not going between 3 and negative 3. That feels like if you thought that the circle was like here and here. Okay, so that one is out. Where on earth has that come from? Okay, well, I've established that I'm rotating a circle around a function, right? If I rotate around an axis. If I rotate a circle around an axis, I get a sphere. And the volume of a sphere, volume equals volume equals 4/3 pi r cubed. Okay, that's pretty close. I know that the radius of this particular circle is 3, so 3 cubed. 3 times 3 times 3, there's a 3 there, so I can cancel one of those 3's out, which is 4 pi r squared, and the r is a 3. 4 pi 3 squared. The answer is A. The answer is A. Okay, what if I couldn't make this circle leap? Can I get the same answer from this? Well, my TI will help me out here because I can find the integral, which is 36. So going back to here, I can say that that integral, don't need that nonsense, that integral there is 36. So I know that the volume is going to be 36 times pi, and I can see up here that 4 times pi times 3 squared, 4 times 9 is 36. So this does give me that answer right there. Okay, does this feel like a trick question? Absolutely it does. Can I imagine you being able to save yourself some time by rotating known shapes around axes? Yes, I can imagine rotating cylinders around axes, rotating rectangles to get cylinders, and so you can just find a cylinder, rotating these semicircles and just finding the volume of a sphere instead of going through the pain of integrating, doing things a little bit smarter. I can also imagine that as part of a larger question where you might be like in a CU situation, you're rotating some object around an axis that requires integration, but you're also rotating some other object around an axis that doesn't require integration. You can do it as a circle or as a cylinder or as a cone if you're rotating a straight line like y equals mx plus c, if you're rotating one of those around an axis. Interesting ideas here. Something to learn. Alright, a complex unfamiliar from Western Australia in 2016. Give yourself about 10 minutes to get it done. And I'm going to start solving it in 3, 2, 1, let's go. So first part of the question is to determine the position vector for point B. Alright, so the coordinates of that point B is what we want. Now what are we told? We've got point S, and we're told what that is. And we're also told that the direction that this laser is moving in is I plus j minus k. So that means that we can find a vector equation for the line SB because we have a starting point and we have a direction that we're moving in, right? So the vector equation is following this formula here, r equals a plus kd. So we'll say vector r is equal to our starting position, -2, 3, 6, plus k times the direction, 1, 1, -1. Okay, so that's the equation of SB. We can write the equation of that line a little bit differently so that it's a little more clear that the equation of that line is giving us a point, like an infinite number of points along that line, right? Just by expanding it and saying that any point along that line SB is going to be equal to -2 plus k, 3 plus k, and 6 plus -k, so 6 minus k. All right, and we can sub in various points for k, and we'll get various points along this line. So we want to know what is the k value such that we'll hit this B point here. All right, so what we want is the intersection of this point and this equation of this plane. So we can just sub this equation of the line, which you can think of as an infinite number of points, into our equation of our plane. So we're going to have -2 plus k, 3 plus k, 6 minus k, dot product, j plus 2k, so 0, 1, 2 equals 9. Okay, the dot product of that, I can just do that. It's this times this plus this times this plus this times this. Okay, so I have a k value of 6. So what does that represent? We have an equation of a line here where this k value is our parameter that moves us along the line, and at a k value of 6 we're going to intersect with the plane. At a k value of 6 we're going to be at our B value. So we're trying to determine the position vector for B. The position vector for B, OB, is going to be equal to this equation if we sub k into it, or this equation if we sub 6 into it, which is the same thing. So -2 plus 6, 3 plus 6, and 6 minus 6. Okay, -2 plus 6 is, I hope it's 4. 3 plus 6 is 9, and 6 minus 6 is 0. Alright, let's stop for a minute, have a look. Okay, I have a clue that I'm correct because my k value is 0 at B, and when we look at our image, it looks like they have drawn B when k is equal to 0. And it's hard to tell the depth here, but it seems like we're supposed to be 4. We're supposed to be out here a little bit, and then it says y equals 9, and we're over here a little bit. So things are checking out. We've got a positive y value, we've got a k value of 0, which our image seems to suggest that might be a good thing, and I'm not sure about this x equals 4 business, but the other two seem right, so I'm pretty happy. Alright, that first part really feels like the warm-up here, because this next part is where it gets tricky. So the question is asking us to determine the unit vector d2, where d2 is in the direction of BR. Alright, so what does all that mean? Alright, so we've got the vector BR here, which is the reflected beam. We want some vector here with a magnitude equal to 1. Okay, so what am I seeing here? Well, what I'm seeing and what I'm told is that this angle is going to be equal to this angle here. Physics students will know that, but we're also told that here. And we're also told that the incoming beam SB, the normal BN, and the reflected beam BR are all contained in one plane. Okay, so we've been talking about this plane a lot, but there's also another plane like that this vector, and this vector all lay on. And that's important because we can do like some two-dimensional vector stuff on those three vectors. The other thing I'm thinking here is that if these two angles are equal, it means that if I had like a unit vector here equal to 1, then the dot actually, let's put it going the other way. If I had a unit vector like that equal to 1, the dot product of b, whatever that thing is, and bn would be equal to the dot product of bn and br, right? Vectors that make the same angles with each other and have the same magnitudes are going to have the same dot products. So that feels like a good place for me to start. The unit vector of bs dot product bn will be equal to bn, the unit vector of br. Alright, so there's it written down. Unit vector bs dot product the normal vector is equal to the normal dot product, the unit vector of br. Alright, so I know the normal vector, I was told that. It's contained within the, it's the normal to the mirror, so it's 0, 1, 2. Now, I can find vector bs pretty straightforward, because I know vector OB is 490, and I know vector OS is negative 2, 3, 6. So putting those together, BS is going to be negative 6, and 6. Okay, so that's that done there. And then this BR thing, right? So the BR, oops, I'll just get rid of that thing there. The BR, that is my unit vector. It's the unit vector that I want to know. And that's just going to be A, B, C, because I don't know it yet and I would like to know it. Now, doing the dot product of this and multiplying by 1 root 108 gives me 1 on root 3. And this bit here, I don't know. But what I can do is do the dot product. 0 times A cancels each other out. 1 times B is B, plus 2 times C is 2C. Okay, this is a useful equation, right? I know that B plus 2C of the thing I want to know is equal to 1 on root 3. There's another equation that I can think of as well for A, B, and C. Because this is a unit vector, we can say that 1 is equal to A squared plus B squared plus C squared. Okay, and that is another useful equation. Too many variables though. 2 equations, 3 variables, so a bit more work to do. Alright, what do I know that can help me? If I come down here, I've got this vector here, this BS vector, or I guess we can call it an SB vector if we want to turn it around. And this normal vector here, and this vector here, they're all in the same plane, right? Which means that I can do like a 2-dimensional vector trick. And I can say, right, some amount of this vector plus some amount of the normal vector will be equal to this vector that I want to know. All right, so sort of nutshelling that, the vector that I want to know, A, B, C, will be equal to some amount of this vector here, SB or BS. It doesn't matter which way I talk about it, right? Let's go with some amount of BS. So -6, -6, and 6, plus some amount of the normal vector there. And we know the normal vector is j plus 2k. Some amount of 0, 1, 2. Taking that together, we can say that A, B, C, the vector that we want to know, is equal to -6x plus 0y, -6x plus 1y, and 6x plus 2y. Alright, so I feel like this feels alright now because we have some equations going on. We know A equals -6x, We know b equals negative 6x plus y, and we know c equals 6x plus 2y. What can I do here? Well, now that I know that a, b, and c all equal those things, I can sub those things into equations 1 and 2. And that's going to give me two equations in 2 variables instead of 2 equations in 3 variables. So 1 on root 3 equals negative 6x plus y plus 2 times 6x plus 2y. And the next one is 1 equals negative 6x squared plus negative 6x plus y squared plus 6x plus 2y squared. Okay, that is two equations, 1, 2, in 2 variables. So if I type these into my calculator, I think as relations, and see where they intersect, that should be good. Okay, 2 equations graphed. We get a nice line for that first one, and we get this weird ellipse thing for the second one. We can find intersection points. All right, there's one about there. Okay, I'll just shift that there. So there's one intersection point. We can find another intersection point about there. Okay, let's bring that back. So now the question is, which of these is our correct x and y value? Which one do we want to use? Probably need to reject one because we're only aiming for one answer, and the x's and the y's are directly related to the one answer that we want. Okay, looking back at this, what I'm finding is something that satisfies this dot product. And this vector here is something that's going to satisfy that dot product. And so is this one, right? Because they're dot products with the same other vector. So one of the x and y solutions, if I sub it into this bit here, is going to spit out this, which I don't want. I already knew it. So let's figure out which one of the solutions will spit that thing out. It looks like... All right, so negative 6 times positive 0.09 will spit out a negative answer. And that's a negative answer there. So I don't want to spit out that negative answer. I'm saying I don't want to spit out that negative answer because I know that if this one's got a negative, then this one's got a positive. I could just sub both in and just test them both. But I'm looking forward and I'm saying, well, if I put a positive in for x, I'm going to get a negative value for my a, and I want a positive value for my a. We can see my arrow is going in that direction. So my hunch is that it's this point that I'm interested in. And so now I should sub that point in to, I guess, this. And subbing that in gives me 0.577, 0.808, and negative 0.1155. And that, believe it or not, is my answer. That is the unit vector. It says correct to 0.01, so I guess I should only be going to 2 decimal places here. 8, 1, and 6. Now, like I said, if I was to sub that in, don't be surprised if it spits out that answer. It definitely will. Now there are other ways to solve this as well. This is the way that I'm choosing to solve this one, but there are other ways to go about it. All right, I'm definitely done with this, and I think I'm done with all of it. So 2 tech active questions, 1 tech active. I think that's enough for this one. 39 questions, same as I did for the methods one. All right, we got, what do we got? Like 36 hours left. Good luck, study hard, have fun.